In this chapter, we're continuing a little bit with mechanics, but we're studying a new phenomenon. Namely, we are trying to explain collisions. In collisions, we basically have two objects involved rather than just one. And we see how these two objects exchange energy and change their velocities due to this impact that they have. I will start with first defining some physics quantities that are used to explain collisions. Namely, these are the center of mass of an object and the linear momentum of an object. And then we're going to use these quantities to describe collisions in various forms. So I'm starting with the definition of the center of mass. The center of mass is basically the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. Namely, it's none other but the point that we used in previous chapters to represent objects and then draw the forces acting on them. But now we're going to be locating it carefully because the location of this point is going to be needed to describe collisions and see how the objects are going to be moving around due to these collisions. So we're going to be trying to locate the center of mass of an object using formula. If we have, let's say, n particles or an object that is made of n parts, they are strung out along the x-axis. If the mass of each particle is m1, m2, so on and so forth, and they are located at x1, x2, and so on and so forth, then if the total mass is m, the location of the center of mass, xcom, is m1, x1, plus m2, x2, plus m3, x3, until you finish with all of the parts, divided by the total mass. So what I'm basically saying here is that the center of mass is where the object's mass is concentrated. To find it, I'm basically finding the average position of all of the parts. And one nice thing is this position doesn't change with variations in forces and so on. It's just related to the mass of the object itself. For objects with uniform densities, the center of mass will simply be at the center. So I could give you some examples. If I had a square, the center of mass would simply be at the center of the square. The density of the object is uniformly distributed, it's just going to be at the center. But if I had, let's say, this kind of arrangement, then I do expect the center of mass not to be at the center of this part or this part. Well, the center here is somewhere up here, but somewhere in between along this line. We're just basically trying to average all of the mass into a single point, and we're trying to locate this point. This is the center of mass of the first part. This is the center of mass of the second part. I can namely here just use this formula to locate the center of mass of this arrangement of two plates. Here, the center of mass is the center. If I had an x-axis, I would just say the center of mass is located at the origin, which is 0. But for this arrangement, things look a bit more complicated. I namely think that maybe the center of mass is somewhere here. To find it precisely, I can use this formula. Let's say the first plate has a mass 1 kilogram, and the second plate has a mass maybe 0.5 kilograms. And let's make an x and y axes to locate the centers of these two objects. So if the first center of mass is at the origin, and let's say the second one was at 20 centimeters, and its y component is at 10 centimeters, I can find the position of the center of mass of this arrangement, of this big plate, to be, according to the formula, m1 x of the center of mass of the first plate plus the mass of the second plate times the position of the center of mass of the second plate divided by m1 plus m2. Substitute that, it's pretty easy. M1 is 1 kilogram. The first center of mass, its x component is at 20. Actually, sorry, C1 is at 0. It's at the origin. So I'll put 0 here. Plus the mass of the second plate is at 0.5. This is the mass times its center of mass is located at x equals 20 centimeters. I will divide by the total mass. One thing I did, I left this in centimeters. I will simply get the center of mass to be in centimeter as well, which is totally fine. So I can calculate this. One thing I want you to notice, I just found the x component. However, the center of mass has a y position as well. It has a certain height. So I can calculate that next by using the same formula applied to the y value. So I got 6.7 centimeters. So it's basically somewhere before the center between 0 and 20. Somewhere here, I would say. Regarding the height of the center of mass, I can find the y coordinate by the same method, m1 y1 plus m2 y2 over m1 plus m2. The first mass is 1, first y component is 0 because I located the first center of mass to be at the origin. This made things easier. Whenever you can do so, just do it. Y2 is 10, and I will divide by 1.5. So I got 5 divided by 1.5. This will be 3.3 centimeters. So it makes sense. I already saw it here because I know the center of mass is along the line between these two. So back to our notes, for objects with uniform density, the center of mass is simply at the center of the object. That was the case for the square. The mass is distributed the same everywhere, so the center of mass is just the center of the object. But for irregular objects, such as the plate arrangement that I did in the previous slide, the center of mass is closer to the denser parts. Let's take a look at what we got. Does this make sense? The center of mass is closer to the denser part. This part here is denser than this part, namely because it has more mass and more area. So the center of mass should be somewhere here in this plate, in this part of the plate, rather than this part. When I did my calculations, the center of mass turned out to be over here. And yes, indeed, this matches with what I saw. The center of mass is closer to the denser part. If no external forces act on it, the center of mass moves in a straight line with constant speed. Makes sense, just like any object we studied before. We used to represent the object to be moving in a straight line in a constant speed where the net force is 0. So here I put all of my formulas. I can also find the z component of the center of mass in case of three-dimensional objects and find the coordinate of each component of the coordinate center of mass. And finally, I can deduce the total position vector of the center of mass. Now, there are some extensions to the formula, namely, if I have a body which does not have a uniform distribution of the mass. Like, let's say a bat is a typical example. In this case, I don't have a constant density, and if I want to find the center of mass, I really cannot add up parts. Like, I cannot take, as in the previous part, here for the two plates, I made one rectangle and one square and took these as two objects and I found their center of mass. But here I cannot really distribute or split the bat into parts and then find their center of mass because this object is changing continuously in shape. It doesn't have a well-defined shape. that I can consider as parts. So to find the center of mass here, I will need to know how the density is changing or how the position is changing according to the mass. So I'm gonna change my formula for the center of mass from a summation to an integral. I will integrate the position over an infinitesimal mass. So I use this formula if I have a changing density. If the object has a uniform density, rho, I can write rho to be mass over volume and rearrange my equations. So one thing I did here, if x of the center of mass is 1 over m integral of x dm, I can take rho, which is the density, it's dm over dv, and it's also m over v. Then dm becomes m over v dv. I will substitute dm here by m over v dv. I'll take the mass and the volume to the outside. They are constant. M and M cancel out. I got 1 over v integral of x dv. This is another formula to use to find the position of the center of mass. So I got
Professor?
a formula that can, 1 second, yes, I'll get back to you. So why am I using this formula anyway? I am using this formula whenever I have different particles, the sums become integrals because they are varying with position continuously. And I can solve this integral or either over the mass or over the volume by substituting the density formula in terms of the volume. So it really depends on the given. If you're given some volume, then maybe integrate over the volume. Yes, Jamal.
Professor Fiege?
Yeah, so I use this formula whenever I have a mass that is varying irregularly. Okay, so you have mass particles that I cannot really add them up as two parts like I did for this plate. Okay, I have actually masses that are varying continuously with position. Then I integrate.
Oh,
So you
okay,
would
thank
see,
you.
let's say I would tell you this object, I give you its variation of mass as a function of position in an equation, and so on. Like usually I don't like to put integrals a lot in the exam, but like in case of simple cases, then maybe, yeah. So let's take a look at an example.
Professor,
Yes.
when we have different densities, which ones do we use?
You have two objects, let's say, made of different densities. You will have to study each one separately and then find the center of mass of these two together after you find for each one. Right?
Okay, thank you.
All right. So let's take a look at this question. This is typical exam level. So I have a uniform metal plate P of radius 2r from which a disk of radius r has been stamped out. So I have this uniform plate and I cut out part of it. So here this is an empty part. The disk is shown in the figure using XY coordinate system shown. Locate the center of mass, COMP, of the remaining plate. So if the disk was still all intact, one thing I know is that its center of mass is simply over here at the origin, right? If nothing was removed. If no parts were removed, X COM and Y COM would be equal to 0 for the disk. That it's simply at the origin. The center of mass is here. So if I had a simple disk, its total mass would be simply concentrated at its center, and the center of mass of this disk is just at the center, which is at the origin here. So its coordinates will be just 0, 0. Now, because I removed this part, so this part is empty, then the mass is more concentrated in this side. And thus, the center of mass is going to be shifted a little bit to the right. This whole object is heavier towards its right part now because I cut out part of it from the left. So the center of mass is somewhere here. I know that for sure. Now, one thing I also showed here in my figure is that the center of mass remained on the x-axis. Why? Because on the y-axis, look at this part and this part. They are still symmetric. So vertically speaking, the center of mass is not shifted towards the upper or lower parts because they are still symmetric. Now the math is gonna show that if you calculate it, but I also see it here clearly. The upper and lower parts are symmetric. The plate with a cut part is symmetric with respect to the x-axis. So y of the center of mass will still be 0 for the plate with a cut part. What remains is to find x of the center of mass for the plate with a cut disk in it. I want you to see the trick that I will do to solve this question. It will be a very nice trick, which is so easy. It will help me in locating the center of mass. What I will do is I'll take the actual plate without removing any part of it. I will say this is none other but, so the center of mass here, x COM of the plate without any cut part is basically equal to x of the center of mass of the disk plus x of the center of mass of the plate minus the disk. So with the disk removed from it.
But Professor,
So
I have
all
a
I'm,
question.
yeah, go ahead, Palisa.
So, like, just doing that numerically automatically places the center of mass to be to the right.
So you don't have to like manually place it to the right. I just saw it like physically, conceptually, I can see that this plate is heavier to the right now because I removed part of it from the left side. But you really don't have to even see it. You can just you can just work with the math and say, okay, the whole plate, this whole plate, without anything removed from it, its center of mass is here, and this plate, this whole plate with nothing removed from it, is equal to this arrangement plus this small part here. That's what I'm basically saying. So I'll study the center of mass. I'll say the center of mass here, which is none other but 0, by the way, is equal to the center of mass of this arrangement with a removed plate, disk removed, plate with disk removed, plus x of the center of mass of the disk, the removed disk alone. Does this make sense? Like this is none other but, yeah, like this plus this arrangement gives you the full disk again.
Okay.
All right, so why am I doing this, by the way? What I want is this, the center of mass of the plate with the disk removed. The center of mass of the plate, which is still a hole, is how much? Where is the center of mass of this plate if nothing was removed? If this whole thing was still intact, its center of mass will be none other but this point, which is the center, which is 0. This is what I want. I'll just leave it. I'll name it X center of mass of the plate with a disk removed. I'll name it P slash D. What I still need is this, the center of mass of the removed disk itself. Let's look at the disk that was removed. Here it is. Where is its center of mass? Definitely it's over here at its own center because it's distributed equally, right? So the center of mass is over here for this removed part. And can you locate this? Can someone tell me what's the coordinate of this point? This point here, what is its coordinate?
Zero
Remy,
R.
can you... How much, Brittany?
0 R.
over 2.
So this point is located, well, this is the origin, right? This is the y-axis, this is the x-axis. So this point is x equals 0. This point will be how much? It is at minus r, because this distance is the radius and it's in the negative part. So I will get minus r here plus xcom. So I can now solve for the position of the center of mass, right? But we need to pay attention that we have an effect for the mass itself. So I have to write here x center of mass of the disk times the mass of the disk. That's my original formula. Here I'll put the mass of the arrangement I'm studying, and I will divide by the total mass. Makes sense? And then I will rearrange these and solve for the position. Let me just show you things in a more tidy manner. So I studied the plate and the disk together, and this is none other but x of the whole plate with nothing removed. And I said the position of the center of mass here should be the center of mass of the plate times its mass plus the center of mass of the removed disk times its mass, and divide by the total mass. And I will rearrange for what? For the position of the plate with something removed out of it. Makes sense? One other trick in this question is I didn't have the masses. So what I did was I said, okay, I don't have the mass, I cannot substitute it, but I know that the ratio of the masses is equal to the ratios of the densities times the volumes. So I used rho equals m over v, same density for both. And then I put the masses ratios. So I said ms over mp will be none other but rho s vs over rho p vp. Densities are the same, they cancel out. And the volumes are the thickness times the area. Thicknesses are the same, areas are different. So this gives me that the ratios of the masses is basically the ratio of the areas. And the ratios of the areas, that's just basically the area of this part and the area of this part alone. So I can find the areas and substitute them. Questions? I'll solve an easier one.
Professor,
Yes, Liam.
after you
So I can solve here another example. I have three particles of masses m1 equals 1.2 kilograms, m2 equals 2.5 kilograms, and m3 equals 3.4 kilograms from an equilateral triangle of edge length A equals 140 centimeters. We want the center of mass of this system. So basically we have three masses and we want to find the position of their center of mass. I'll just write down first the formula. X of the center of mass will be m1x1 plus m2x2 plus m3x3 over the total mass. I have three objects, three masses. I want to find their center of mass. I'll take the position of each mass, multiply it by its own mass, and add these up and divide by the total mass. That's how we find the average location of all of these three, which is basically the center of mass location. The first mass, m1, is here. It is at the origin, which means that m1 will have x1 equals 0. The second mass, m2, is here. It's on the x-axis at a location. Let's see, this is 150 over here, and I have 100 here. So this is 110, 20, 30, 40. So m2 is at x equals 140. We are given the measurements, by the way. We don't have to read them. m2 is at x equals 140. So I can put m2, which is 2.5 kilograms, times 140 centimeters, plus m3 is 3.4 kilograms, and its x location is given by 70. I will divide by the total mass, which is 1.2 plus 2.5 plus 3.4 kilograms. I just added up all of these masses. I can calculate this. You should get 83 centimeters. I left these coordinates in centimeter, and then I will get my final answer in centimeter, which is preferable. I'm trying to find the position of the center of mass. It's convenient to have it in the same unit as the constituent points. So we found the x-coordinate of the center of mass, but this center of mass is also going to have a y-coordinate, namely because these 3 points are located in an xy plane, and their center of mass is somewhere here within this triangle. So it will have both x and y components in its position. So I will do the same formula, but along the y direction. It's just the same formula, but instead of x, I'll put y, and I will solve for the center of mass. M1 is 1.2. M1 is at the origin, so its y component, its y position is also 0. M2 is 2.5, and M2 is at the x-axis, so it has y equals 0. It's already given to us in the table. This made things easier. M3 is 3.4, and its y-coordinate is over here, which is 120, also given in the table. I'll divide by the total mass, and I will calculate this. You should get 58 centimeters. So the center of mass is basically at 83, 58. I can locate that, by the way. This is 100. 83 is somewhere here. So this is x. And the y component is at 58. Here it is. So the center of mass of this triangle is somewhere here. It's a bit shifted upwards over here. Why? Because M2 and M3 are larger than M1. So the center of mass is closer to M2 and M3. You can see how the physics always matches with the math. So in addition to locating the center of mass, I could be interested in the forces acting on the center of mass. And one particular thing we notice is if I have an object and it's moving, it's a system of particles. Let's say this object is a system of particles. F net is going to be equal to the total mass of all of these particles times the acceleration of the center of mass of these particles. And that is a very important observation with very important impact. Let's say my system starts here. Let's say I have a combination of 10 balls. I threw 10 balls in a projectile motion. And as these balls move, they fragment apart from each other, such as this fireworks rocket, actually, which explodes in flight. So the rocket was moving as one object, but then it explodes. A very important impact of the center of mass is that the center of mass of the fragments will continue to follow the original parabolic path of the rocket until the fragments start to hit the ground. All the way here, the fragments will have their center of mass solely along the parabolic path. And this is at the heart of our study of collisions, by the way, because in collisions, I will consider the two colliding objects to have their center of mass always at the same location. And it will help us in solving for the locations of the objects before and after collisions. Now we can proceed to the second quantity we're defining in this chapter, which is the linear momentum. The linear momentum of a particle, it's a quantity similar to the force, the velocity of an object, the density of an object. The linear momentum is a quantity that is defined to be the product of the mass and the velocity. So I have here the mass of the object and the velocity vector. And because the velocity vector is a vector and the mass is a scalar, the obtained linear momentum is a vector. Its unit will be kilograms meters per second, just the product of these two units. One thing I know about linear momentum, in addition to this formula, is the time rate of the change of the momentum of a particle. The change of the linear momentum with respect to time is equal to F net. I want you to see where this comes from. I'm writing that F net equals the change of the momentum with respect to time. Now the momentum is m times v. The mass doesn't change with time. Take that outside. What remains is dv over dt, which is none other but the acceleration. I got F net is equal to ma. This is Newton's second law. So from Newton's second law, I got another form, which is in terms of the linear momentum. You can see how different objects will have different linear momenta. Namely, these three objects have the same speeds, but they have different masses. The one with the larger mass will have the highest momentum. What's the impact of that? Well, like I told you, we are studying the center of mass and the linear momentum as an introduction to the study of collisions. And we will see that an object with higher momentum will make a bigger impact in collisions. And that makes sense. A large truck collides with a small car. The truck will give more impact on the car. It will have higher momentum that it's carrying with it because of its larger mass. Now, if the car was too fast, it might actually have almost the same momentum as the truck. So there are two factors which will affect this impact of collisions. One is the mass, the second is the velocity, and these two are embedded in the linear momentum. So I will solely say collisions are determined by the linear momentum of objects. And the linear momentum is given by the mass times the velocity. And F net is equal to the change of the linear momentum with respect to time. So let's take a look at a study of collisions. So one thing we know is if there are no net forces acting on the system, I will say the linear momentum P does not change. This comes from the fact that I just said
Professor
net. Yes.
نحن كنا 9.4 سنة 9.7 الباقي ما بنعملهم ولا
No, I will do it next time. I wanted to
okay.
describe collisions before the previous parts.
Okay,
And
okay.
I'll get back to these, but this is solely because of the restations, to be honest, because I want you to be able to solve some problems in restations. But I'll get back to that slide next time, all right?
Okay, thank you.
Yeah. So I'm gonna be going back to the definition of the impulse. It's another quantity that we will study, but I will do so after I define a little bit on collisions, so that you can solve a little bit on collisions during the restations. So yeah, so because I said F net is equal to dP by dt, the variation of the momentum with respect to time, then if F net is equal to 0, no external forces are acting on the system, then P should remain constant. And this is at the heart of the study of collisions. I will say the linear momentum is conserved if there are no external forces acting on my system, and I can solve some examples on these where I will take the linear momentum to be conserved for a system of particles. I have two particles, for example, here I have a hauler with a module, and then this hauler ejects its cargo module during its launching, and when it ejects it, it's as if it lost part of it. And the question is, we want to find the volume, the velocity of this part when it's released. I study conservation of momentum and I work through it. I say the total momentum is conserved. Initially, the momentum was for one system, the whole rocket, along with the module that it was carrying. After releasing the module, the linear momentum will be a sum of two values, one for the rocket alone and one for the module. So I will say P initial equals P final. P initial is the total mass of the rocket with the module times its initial speed. P final will be for each part separately. So I'll take the mass of the module, which is 0.2 of the total mass, times its speed, plus I'll take the whole mass here of the rocket alone, which is 0.8 of the total mass we had earlier, times the speed of this rocket or hauler. I was given the hauler travels 500 kilometers per hour faster than the module along the x-axis. So the relative speed between them is 500. So here I had to use some relative speeds. So I wrote it down. I said the hauler relative to the sun or relative to the sky, its speed is the hauler relative to the module plus the speed of the module relative to the sun. So I got this relationship between them. If I already had this speed given to me, the problem would have been easier, okay? I'll work through this next time. Maybe we should stop for today.